Hi, this is part 2 of this lesson. For the first part, refer to the YouTube channel. So I'm going to continue where I left off in lesson 7. And so the last thing we talked about was the plus minus theorem, theorem 4.5.3. And so now let's just look at example 4 of section 4.5. Okay, so in example 4, we have the polynomial piece of 1, which is 1 minus x squared. We have the polynomial piece of 2, which is 2 minus x squared. And we have the polynomial piece of 3, which is x cubed. Okay, these three polynomials as vectors in piece of P3 are linearly independent. Okay, so you can show that these three polynomials are linearly independent. So let's show why that is. Okay, so this is because P1 comma P2 is linearly independent because neither P1 nor P2 is a scalar multiple of the other. Okay, so P1 and P2 are not scalar multiples of each other. They're also non-zero, and both are non-zero. Okay, and so that means that from the previous theorem, that means this set is linearly independent. So this is linearly independent set because neither P1 nor P2 is zero. And neither of them are a scalar multiple of the other. Okay, so that's a linearly independent set. Now P3 is not in the span of the set P1 comma P2. Okay, so the polynomial piece of 3, which is x cubed, is not in the span of P1 or P2. Right? P1 and P2 are polynomials of degree 2, and so x cubed is not a scalar multiple of P1 and P2. You can only have a degree of most x squared. You don't have x cubed anywhere there. So P3 is not in the span of that set. And so therefore, by the plus minus theorem, we can say that the set P1 comma P2 union the set containing P3, which is the set P1, P2, P3, is linearly independent as a set, right? So the set P1, P2, we've found was linearly independent, and P3 is not in the span of that set, and so we can add P3 to the set, and we still have a linearly independent set. And so this set is linearly independent, and we show that using the plus minus theorem. Okay, so that's example 4. Okay. So theorem 4.5.4, let capital V be an n-dimensional vector space. Okay, be n-dimensional. So V is an n-dimensional vector space, and S is a set in capital V with exactly n vectors. Okay, then capital S is a basis for V if and only if S spans V or S is linearly independent. Okay, so let capital V be an n-dimensional vector space. Capital S is a set in V with exactly n vectors. Then capital S is a basis for V if and only if S spans V or S is linearly independent. Okay, so what this theorem adds is that a basis for a vector space is equivalent normally to spanning and linear independence of the set. But with the given information that V is n-dimensional, S is a set in V with exactly n vectors. So given that V is n-dimensional and S is a set with exactly n vectors, right, where n is the same amount as the dimension of your vector space, given that information, we only need to know that S spans V or that S is linearly independent, one or the other, in order to imply that it's a basis, in order to be equivalent to being a basis, right? So once you know your set has exactly the same number of vectors as the dimension of your vector space, then instead of requiring both spanning and linearly independence, you could choose one or the other, and it's equivalent to being a basis, okay? And so this actually makes the job of finding that a set is a basis shorter, because you only have to prove one of the two. But that's only if the number of vectors in your set is the same as the dimension number of your vector space. And that's theorem 4.5.4. Okay, and so, so in example 5 in this section, V1, which is -3, 7, and V2, which is 5, 5, those two form a basis for R3. For R2. Okay? So those two vectors form a basis for R2, and we can show that using theorem 4.5.4, because we have two vectors. So if the set S is the set V1, V2, this set has exactly two elements in it, two vectors in it, and R2 is two-dimensional, right? So the size of S is the same as the dimension of R2, and so we only need to show that it spans V or it's linearly independent to show it's a basis for V equals R2. So if S is linearly independent, then S is a basis for R2. But this is by theorem 4.5.4, this theorem. Because otherwise, without this theorem, we would also have to show it's linearly independent, right, by the definition of a basis from last video, in part 1 of this lesson. Right, but by this theorem, we only can show one or the other. We only have to show. So if that happens, then S is a basis for R2 and we're done. Okay, so the goal now is just to show S is linearly independent. But now S is a set with two vectors in R2, and neither is a linear combination of the other, which means it's linearly independent. So capital S is a set of two vectors in R2 such that neither is a scalar multiple of the other. Okay? And both vectors are non-zero. Okay? So capital S is a set of two vectors that neither is a scalar multiple of the other, obviously, right? And both vectors are non-zero. And so that implies S is linearly independent by a previous theorem also. Okay? So capital S is linearly independent, and we showed over here that if we can show S is linearly independent, then it's a basis using the above theorem. Okay? And that's example 5, and it's an application of the theorem at the top of this board in solving a problem. Okay? And so that's example 5. Okay. So theorem 4.5.5. Okay, let capital S be a finite set of vectors. In a finite dimensional vector space, capital V. Part A, if S spans V, but is not a basis for V, then capital S can be reduced to a basis for V by removing the appropriate vectors from S. So this theorem doesn't say which vectors you remove, and it doesn't say how many, but there's some number of vectors, and there's a certain choice of vectors to remove from S, that if you remove those vectors, then S will be a basis for V, right? Okay, so if S spans V but is not a basis for V, we can remove the appropriate vectors from set S to make it a basis. And that's assuming S is a finite set of vectors in a finite dimensional vector space V. Okay, B. The same assumptions, but part B, if capital S is linearly independent as a set, but not a basis for V, then S can be enlarged by adding the appropriate vectors from capital V to it to make it into a basis. Okay? So if capital S is linearly independent but is not a basis for V, then S can be enlarged by adding appropriate vectors from V to it to make it into a basis. So it can start out as not a basis, but linearly independent, and we can add the appropriate vectors from the vector space V to the set to make it a basis. Okay? It's linearly independent, but doesn't span the set. We can add the appropriate vectors to include the condition on the set, the added set that is also spans the vector space, and turn it into a set that is a basis. Okay? And so theorem 4.5.5 is a theorem where if you have a set that's not a basis for a vector space, there's ways where you can add or remove vectors from it to turn it into a basis for that vector space. But there has to be certain given information that holds in that situation. If things work out just right, if you have a set that's not a basis, there are ways by adding or remove appropriate vectors to turn it into a basis. Okay? And so that is theorem 4.5.5. Okay. And so there's one more theorem in section 4.5. Okay. And that's theorem 4.5.6. Okay. So I'm actually going to use this green. I'm going to use this green marker now. I'm running low. Theorem 4.5.6. Okay. If W is a subspace of a finite dimensional vector space capital V, then the following are true. A. W is finite dimensional. B. Dimension of W is less or equal to the dimension of V. And C. W equals V if and only if the dimension of W is equal to the dimension of V. Okay? So this is theorem 4.5.6. Okay, so if W is a subspace of a finite dimensional V, then W has to be finite dimensional. The dimension of W has to be less or equal to W dimension of V. And W equals V, that statement, is equivalent if and only if the dimension of W is equal to the dimension of V. Okay? Okay. So that's the end of 4.5. If you think of a plane in R3 as a subspace of a plane going through the origin in R3, that would be a subspace of R3. But then if you think of a line through the origin, in that plane, that would be a subspace of the plane. Okay, and the dimension of the line would be 1, and the dimension of the plane would be 2. So just to illustrate that idea, if you have R3, and here's the x-axis, y-axis, and z-axis, we learned from an earlier lesson that a plane through the origin in R3 is a subspace of R3, and so that's a vector space, right? The plane going through the origin in R3. Any plane going through the origin in R3. So that plane that I drew there is a subspace, right? And so the dimension of this plane turns out to be 2, and the dimension of all of R3 is 3. And so this dimension of the plane is less or equal to the dimension of the entire all 3 space. But then if you take a line, like I was just saying, if you take a line L, this is the plane P, that's the line L. Line L is on this plane, and so as the plane goes out in all 4 directions, the line stays on that plane. The dimension of the line is 1, and the dimension of the plane is 2. And the line is a subspace of that plane. And so the dimension of L is less or equal to the dimension of P. Okay? And so you see from this illustration how that theorem happens in this example. Okay? And so that's the end of 4.5, and now next is 4.6. And 4.6 is on change of basis. Okay, and so this is a topic that people often have trouble with. Okay, if S is equal to the set V1, V2, up to including V sub n, is a basis for finite dimensional V, finite dimensional vector space V. And if coordinates of V relative to S is equal to C1, comma C2, comma dot dot dot, comma C sub n, and that's the coordinate vector of coordinates of V relative to S, then the function slash map V to the coordinates of V relative to S creates a one-to-one correspondence between vectors in V and vectors in Rn for some n. Okay? So that's just numbering it. So that's the function, okay? And so that map 1, that function that maps V to the coordinates of a vector V to the coordinates of V relative to S. 1 is the coordinate map relative to S. Okay? So that function is the coordinate map relative to S from V to Rn. Okay? So we will denote the coordinate vectors of V relative to S in matrix form. There's more than one way to do that, represent it. This is one way to represent it, and this would be in matrix form. So that's coordinates of V relative to S in matrix form, where the coordinates are elements in a column vector with n components, an n by 1 column vector. Okay? Okay, so this map creates a one-to-one correspondence between the vectors in V and vectors in Rn. So I've drew this picture before. I'm going to draw it again. And so this is V, and this is Rn. And so if you take a vector of little v in the entire vector space capital V, and you think of its coordinates relative to S, the one-to-one correspondence between capital V and Rn is that if you take any vector in little v and capital V, it corresponds with its coordinates relative to some basis S, right? Where S is a basis for a finite dimensional V, okay? And so every vector in V has its own distinct coordinates relative to this basis S. And so you're just associating all of the vectors in V with exactly one coordinate relative to basis S. And so without the coordinate language, you're associating all the vectors in capital V with an n tuple in Rn. Okay? And by that same correspondence, you're taking every n tuple in Rn and associating it with a vector in V. So this is an exact correspondence between the two. For every element in one, it corresponds with exactly one in the other. Okay? And so we're going to use this later in the section. Okay. Good. Okay, so there's something called the change of basis problem. Okay, so this is a solution to what's called the change of basis problem. If we change the basis for a vector space capital V from an old basis Sorry, okay, the camera. So this is a solution of the change of basis problem. If we change the basis for capital V from an old basis, B prime, which is equal to the set U1 prime, comma U2 prime, comma dot dot dot, comma UN prime, to a new basis, B, which is U1, comma U2, comma dot dot dot, UN. Then for each little v in vector space capital V, the old coordinate vector which is this, is related to the new coordinate vector by the equation coordinates of V relative to the new basis is equal to the transition matrix called capital P times the coordinates of the vector relative to the old basis. So this is equation 7 in 4.6. Okay? So if we change the basis for V from an old basis B prime to a new basis B, then for each little v in capital B, the old coordinate vector is related to the new coordinate vector relative to B. Relative to B prime and B respectively. The old coordinate vector and the new coordinate vector are related by this equation, where P is equal to the transition matrix here. Okay, where the columns of P are the coordinate vectors of the old basis vectors relative to the new basis. Or, in other words, it's the coordinates of U1 prime relative to B, U2 prime relative to B, dot dot dot, the coordinates of UN prime relative to B. Okay? So this matrix P, its columns, the first column is the coordinates of U1 prime relative to B, The second column is u2 prime relative to b, dot dot dot, the last column, the nth column, un prime relative to b. Those are the n columns of P. Okay? Right? The old basis is B prime. That's the old one. Right? B prime is the old basis. B is the new basis. And so the columns of P are the coordinate vectors of the old basis vectors. The old basis vectors are u1 prime, u2 prime to un prime. And so we're taking the coordinate vectors of each old basis vector relative to the new basis B. And so the coordinates of the old vector u1 prime relative to the new basis B, that's the first column. The coordinates of the old basis vector u2 prime relative to the new basis B, that's the second column. Up to in the last column, which is coordinates of the last old basis vector relative to the new basis. Okay? And so each of these is just finding the coordinates of a vector relative to a basis, right? The vectors u1 prime to un prime are each just vectors in the old basis. And so you're just taking each vector in the old basis and finding its coordinates relative to the new basis. And those are the corresponding columns of your transition matrix. Okay? So you're just taking each vector in your old basis and finding its coordinates relative to your new basis. Okay? So if you know how to find the coordinates of a vector relative to a basis, then you just take each of these and find its coordinates relative to your new basis. And those are the columns of your transition matrix, P. Okay? Okay? And so once you find P, then by multiplying that by P, you get that. And so that's the relationship between this and that, between the coordinates of a vector relative to an old basis B prime and a new basis B. Okay? Okay? Okay, so then that's the idea. Okay? So you might want to pause the video, you might want to think about this a little bit. But let's okay, and then let's keep going. Okay, so the P there is a transition matrix from old basis to new basis. Okay, so this notation, this is the transition matrix from an old basis B prime to a new basis So that's the transition matrix from an old basis B prime to a new basis B. Okay? And so that's the notation for it. Okay? So the transition from an old basis B prime to a new basis B, that's going to be the matrix whose column vectors are the so each of these guys are right. This is the first component of the old basis vector, and you're going to find its coordinates relative to the new basis B. And then these are the coordinates. This is the coordinate of the second old basis vector relative to the new basis B. Dot dot dot. And then the last coordinate vector relative of the old basis. Last vector of the old basis relative to your new basis B. Those are the columns of the transition matrix from the old basis B prime to new basis B. And the transition matrix from B to B prime, that's equal to the coordinates of the first basis vector relative to so this is your old basis here, and this is your new one, right? But it's not by the prime or without prime. It's the thing to the left of the arrow is the old one, and the thing to the right of the arrow is the new one, right? And so this notation is kind of hinting that the thing to the left of the arrow is the old thing, and then you're transitioning to the new thing there. And so if you switch the order of these things, the roles change. And so now this B is the old basis vector, and that's the new one, right? So where before B prime was the old one and B was the new one, if we switch the order here in the notation, we're referring B as the old one and B prime as the new one. And so you would now want the first old basis vector, which is u1 now, without the prime, because it's in B, not B prime. And you would want the first basis vector in your old basis B and its coordinates relative to the new basis B prime. And you continue in that pattern, and you'd have u2 relative to B prime, up to including the last one, which is un relative to B prime. And so these are the coordinates of each old basis vector B relative to the new basis B prime. And so those are the columns that will make up the transition matrix in those two. Okay? And so this is equation 9 and 10, respectively, in section 4.6. Okay? So as a summary of all that other stuff I said, you can kind of look at what's in this box. You should look at the other things too, but if you focus on what's in this box, it can help you to understand a transition matrix and the relationship between the coordinate vectors of old with respect to an old basis and a new basis, right? The goal is to understand this equation where you have something like this, right? Where this is the old basis and that's the new basis. So actually I'm going to put the prime over here. The goal is to understand that equation, right? But inferred in this equation is that this is the old basis and this is the new one. And so if you switch the roles of the old and new one, you'd have to switch the B and B prime there. Okay? So if you start with its coordinates of vector relative to an old basis, you have to left multiply by the transition matrix P to get its coordinates relative to a new basis. Okay, so example 1. Okay, so for example 1, we want to consider the bases B, which is the set U1, U2, and the basis B prime, which is the set U1 prime, U2 prime. Where U1 is 1, 0. So B is that, and B prime is that. Where U1 is that, U2 is that, U1 prime is that, and U2 is that. Then let's find the transition matrix